Hello, today I would like to represent about compensator design. So the topic that I selected, which is the first one is PI and PD design. So let's go with the first topic that I have selected, which is PI and PD control. So we would like to start to talk about what is PI and PD controller. So first let's get started. PI and D. P is proportional control, which is the form of feedback control. It is the simplest form of continuous control that can be used in closed loop system. This control is a controller that responds a few minutes faster. So the next one is I, which means that integral control. Integral control is a second form of feedback control. It is often used because it is able to remove any deviation that may exist. I controller are much slower in their response time than P only controller because they are dependent on more parameters. So the last one is D, which means derivative control. It is a form of feed-forward control. If the primary benefit of the controller is to resist change in the system. So let's get started. What is the PI and PD controller? So the PI controller is provide a faster response time than I only due to the addition of proportional action. PI control can stop the system from fluctuating, and it also able to return the system to its set point. So the PI method that which is we adding the zero and pole in the system, and it will make the steady state error go to the zero. And the next one is PD. PD is a combination of feed-forward and feedback control because it operates on both the current process condition and related process condition. So the method of the PD control will add the zero to the forward to the plan or the system. So the benefit of the PD can make the shorter response time and improve the safety state, but not greater than PI control. So this is my selected transfer system which have a third order in the type 0 system. So let's get started with the MATLAB with finding the uncompensated value. This is my program, and I would like to find solve it for you. So start with the uncompensated, which have I selected to overshoot with 24.5%. which having damping ratio equal to 0.008 from the calculation from the which is this which having damping ratio is 0.458. So let's finding the value by Lucas method. So from the damping ratio 0.458, we having pole and gain, which we will have pole and gain is here. Yeah, yes. And then we will find the function to find the response time of the system. So first I finding the feedback and find the step. I use the gain and function gain, which means a k from the system, which is this, and g is the function or function. So here we get all the feedback function of the system. So this is the function of the system, which having the peak time, settling time, and the steady state error with final value time. So let's get started with the first control, which is PI control. So my objective is to improving steady state error to the zero, which means no error in the system. So I designed the compensator PI form. So firstly I still from the calculating from the I assume the zero that adding in the system, which is 0.6, and you will get the new function. I adding number pi. I add pi system into the adding into the system. And then I step locus and find the damping ratio point in here. My system is not specific the 0.4 damping ratio, so I use the damping ratio this. I use and after that I count the feedback to the system and the response graph and comparing with graph of compensator, the system with after compensator and system without compensator. So this is the result that I calculated. I use the program to solve. You can see that the from response in the system after compensator, the final value should be 1, which means that the steady state which is 0. You can see that the final value before and after is not the same. Yeah. So that is for the PI controller. Save it. And the next one is for the PI controller. This is the file that I need. I try to complain about it. So the next is PD controller. So the objective of the PD controller, which is to reduce the setting time by half. So the first I have the uncompensated value. I use the pole from the Ludocast in uncompensated to calculate the setting time of the uncompensated. So I use the formula, which is 4 by the 0, which is the formula from the time response topic. So I get 1.60 seconds, which is system before compensate. So and therefore then I get the new setting time, which is that our objective, which is by half. If you get the 0.815 seconds. So and then I have to calculate the design point to use to calculate the PD compensator. So first I calculate the zero first. I get 4.9, and then I use the trigonometry theory to calculate the pole, and then I get the pole, which is the 10.96 imaginary, and then I have the design point. After that, I plot it into the graph and use the system function to be calculate the 0 point, the 0 point. Yes. So this is by I calculate the 0 point by Ludocast theory. This is use the knowledge about trigonometry, the main, and then I get the 0 point, which is 79.29. Yes, the compensator of the PD is S plus 29.29, which is to time with the system function. So let's get started. So this is the system before and compensate. And then this is the best one before out and compensate. This is all the system before and compensate. So and next I adding the numerator PD and denominator PD, which is the mean by this. It is this value. Yeah, this value. Oh, okay. Okay, and I run it again. Yeah. This is S plus 29 by 529. And then I time it to the system. It will get this value CPD X. I finding the result, finding the gain point by the root locus. Okay, run. Okay, this is the point. Finding the point of the damping ratio. And here is point is 5.45 gain with the 0.409 damping ratio. The next one, okay, the 0.409 is the nearest point. Sorry, I can't recognize the gain point. This is 4.44. Okay, 544. Okay, the next I find the response of the system after compensate. Okay, this point setting time. Yeah, the setting time will be 0.685, which is reduced from the system before compensate. Comparing to the first one, the system compensate. Yeah, you can see that the setting time is reduced by half. You can see the system before compensate is 1.39 and the system after compensate is about 0.685 seconds. So you can see that the system is reduced within the objective that we expect. So the conclusion, the PI and PD controller are both the feedback control strategy using control system. They differ in how they respond to error. A PI controller use both proportional and integral term, which PD use proportional and derivative. PI are effective at eliminate steady state error, make them suitable for application where precise set point taking is crucial. PD controller, on the other hand, are better at damping oscillation and reducing overshoot, making them useful in system with fast dynamic and where stability is a priority. So, thank you for listening. I'm Natakorn with the student ID 6410755 026. Thank you for attention.